Hello, students. It's so good to get to be with you a little bit again. I'm sorry I can't see your faces, but I sure am excited to get to talk to you about our Day 29 AMI assignment. Now, I've come up with a problem that's a little different than the one that you're going to see on the assignment. Don't want to give too much away, but this will give you hopefully a great picture of what it is that you need to do on this assignment. For the picture that I have here, for this graph, we are talking about a ball that has been thrown from the top of a building. It says the graph represents the height y of a ball x seconds after it's thrown into the air from the top of a building. So we had some little gal or guy who walked up to the top of the building and stood there, threw his or her arm into the air and threw the ball in the air. And so as time is passing, this is our time in seconds, as time is passing, we're measuring the height of the ball. So the ball starts at this height. This is at 0 seconds. So that's when the ball is thrown. This is actually a height of 64. So it starts at a height of 64, and as time is passing, we're measuring the height of the ball, the height of the ball, and the height of the ball until we get down here and the ball hits the ground. So we're measuring the height of the ball at each increment until the throw is over. The ball hits the ground. So the first question that you are asked is, hey, given this time and this time, at which time is the ball higher? So let's talk, let me just give you a couple of times. Let's say at 2 seconds and 2.5 seconds. So we're gonna compare the time at 2 seconds and the time at 2.5 seconds. So we might actually call that comparing y of 2 and y of 2.5. So this is y of x, or f of x, so we called it y here. So we want to know at 2 seconds and at 2.5 seconds. So we go to 2 seconds and we take a look at how high the ball was at 2 seconds. It was up here. And then we go to 2.5 seconds and we look at how high the ball was here. Our height at 2 seconds, it looks like it was somewhere around 95 feet. And our height at 2.5 seconds, it looks like it was somewhere around 85 feet. And so we see that it was higher at 2 seconds. And we can say that we know that it's higher at 2 seconds because it was at 95 feet versus 85 feet. Or we could also say, hey, the graph was higher at that time. I see that the graph was higher. And so mathematically, you can say, hey, yes, it would be higher here because of how high was it? It was 95 feet. The graph was higher. The second thing that you're asked to do on this problem is to tell us, when was this ball at its highest? What time was the ball the highest? Well, that means we're looking for the vertex. If you remember that word, the vertex, that's our turning point. When if our parabola opens up like a cup, then we're looking at that lowest point, and then it turned and started going back up. Or if it's down like a frown, we're looking at the top, the highest point where it started, and then it started coming back down after that. So this is asking for the highest. When was it the highest and how high was it? So I'm going to, again, follow my picture here, and I see that I'm going up, 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 turn, down, 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 down. And so this must be my highest point. That must be my vertex. So the question is, how high was it and when did it happen? So I'm going to take a look and look at my vertex, look at my graph, and I see that this is go across here to see how high it is. It's 100 feet in the air. And then I want to see when did it happen. So I'm going to come down here to time, and it happened at 1.5 seconds. So we can say at 1.5 seconds, the ball is at its highest point, or at its highest of 100 feet. So 1.5 seconds, 100 feet. So that gives us our highest point. The final piece that no, not the final piece. I forgot. There's a third piece before we go to that fourth and final piece. The third piece asks us about the domain of our graph. Let me remind you that domain is our set of x's, our x values. So we're looking across here, and we want to know, when does this problem start and when does this problem stop? That's really what the domain is asking. When does it start and when does it stop? Well, we're throwing the ball. So it's when is the ball thrown and when does the ball land? And so we take a look, we know that it's thrown here. Well, what time, from my x's, what time is it thrown? It's thrown at 0 seconds. So our domain, our x's are going to start at 0. And when does our throw end? Well, it ends when that ball hits the ground over here. When the height of the ball is 0, and so it ends at 4 seconds. So we can say all of our x's occur between 0 and 4 seconds. We have a point at 4 seconds, so we're going to put an equal to sign there. We have a point at 4 seconds, so we're going to put an equal sign there. And so this entire throw occurs when 0 is less than or equal to x is less than or equal to 4, between 0 and 4 seconds. For those of you who are using interval notation, because we're using equal signs, we would use brackets, starts at 0, ends at 4. All right. So the last thing they ask us to do is take a look at some equations and see which one is going to work for this picture, and if it doesn't work, why not? What is it that's wrong with the equation would make it not work? Well, each of the equations that you're given is in vertex form. So let me remind you that vertex form is y is equal to a times x minus h quantity squared plus k. So we want to pay attention to our a, our h, and our k. Our a is our vertical stretch. One of the things that we did a lot to find a was using out 1, up 1, out 2, up 4, or out 1, down 1, out 2, down 4. That's going to be really hard to do with this particular graph because of our numbers here on our y-axis. However, we can tell whether that A is going to be positive or negative. Let me remind you that if A is positive, our parabola opens up like a cup. If our A is negative, our parabola opens down like a frown. So use that to decide. That's one of the things you need to look at on those equations that you're given on this particular day's work, to decide which equation might be true. For this one, because we're opening down like a frown, we know our A is going to be negative. So we know that if we are looking at an equation and it doesn't have a negative right here, then it cannot be the correct equation because the parabola is not opening the right direction. Now, we don't know exactly what A is, but we know about that negative. Now, this H, if you'll recall, is your horizontal shift. How far did we shift left or right from the parent function, which has the vertex at 0, 0? So if our vertex from the parent function sits here at 0, 0, and this vertex is over here, it's over and up, then that means that our H is going to be different. So we know because we looked at it earlier that our vertex shifted over from 0 to 1.5 seconds. So that means that we're going to have a 1.5 right here because that's our horizontal shift. Now, there's a minus sign in here, and we shifted to the right, so we put in a positive 1.5. So if you put a positive in here, that negative's not going to change. Remember, insider's lie, so we're looking at an opposite sign situation. The K is our vertical shift. How far did we move the vertex up or down from this 0, 0? Well, after we moved it over here, we moved it way up here. We said it went up to 100. And so that means that we're going to have a plus, sorry about the dog, a plus 100 because it went up 100. So use these ideas of A, H, and K to decide which of the equations would work. And if it doesn't work, why not? Is it the A, the H, or the K that's wrong? And tell us why. What's wrong and why? Have fun working on this. Thanks for letting the dog bark. See you soon.